Okay, good morning. Let's get started lecture 2. So, yesterday we had seen some very basic introduction to embedded systems and real time systems, and we had said that embedded systems constitute majority of the real time applications, but of course, real time systems are not confined to just embedded applications, application also elsewhere, as we will see later. Yesterday we had seen some example applications of real time systems, embedded systems, and we had seen a basic structure of the embedded systems, and we had said about different types of sensors, actuators, and then these signal need to be conditioned, and then there is a computer processes these human interface to configure and control. So, let me just ask one or two questions before we get started, just to check that you are following the course. So, can you just name one or two sensors and the principle on which these are based? Anybody would like to name just a sensor? Which can be? Temperature sensor. Okay. So, what will be the principle on which it will be based? Okay, thermocouple. Any other sensor? Okay, light sensor. So, what will be the underlying principle? Right. So, photovoltaic electricity. So, that is the principle. Pressure sensor. So, what will be the physical principle behind that? How? I mean, you just apply pressure to anything, you do not convert to electricity, is not it? So, what is the piezoelectricity. Okay, fine. So, let us proceed further with our discussion. So, today we will look at some very basic characteristics of real time systems, so that when we start discussing about the operating systems, we will keep these in mind. So, I will just have one or two slides which I had already seen yesterday, just for continuity. We had said that a system is real time when we describe the behavior of the system, we need to express time quantitatively. But the question is, how do we express behavior of any system? Suppose you are asked to describe the behavior of a system, let us say anything, maybe a mobile phone or something. So, you are asked to describe, given a system, you are asked to describe the behavior. So, what will you do? How will you describe the behavior? Yeah. The behavior is given in terms of the input output behavior basically. So, what are the functions it supports? The function, each function would basically require some input, and then that will produce some output. So, we have to list out all these functions and the kind of input and output, and if such description of the behavior requires some quantitative notion of time, we have a real time system, but every function may not be real time, that we have to keep in mind, right. I think as we proceed, this point will become clear. So, this diagram just shows that there are events that are recognized by sensors in embedded system, and the processor processes these and produces external output. Just an example is a automobile system. It is seen that whenever the sensor detects a collision, will be processed, and what needs to be done, inflating the airbag and ejecting it, will be done in 10 millisecond or less, otherwise the system will fail. So, yesterday we were just observing this diagram, very basic diagram, but we have to keep this in mind as we proceed. So, the kind of systems that we will be talking of, there will be a CPU which will be getting data from events from sensors or maybe data, and converted analog to digital conversion, and then read by the CPU. and these are processed by the software, and output is produced, and the output is converted and drives the actuator, can be a motor or can be a hydraulic pump or whatever, and we will have some memory in the system. As I was saying that in these kind of systems, we will not really have magnetic memory, very rare in an embedded system to have magnetic memory. These are normally semiconductor memory but as we know that semiconductor RAM memory is volatile. So, how do you store permanently data? ROM is not being used very frequently now, it is getting obsolete. We have flash memory. So, flash memory like your pen drive, no, you have gigabytes of memory available in flash memory. So, what exactly is a flash memory? Just to get things right, because later we won't see those hardware details. What exactly is a flash memory? For example, your pen drive, what is it? Semiconductor, but what kind of semiconductor? Is it a ROM? Is it a RAM? Is it what is it? Sorry, can you please repeat again? Permanent. But how can you get a permanent memory in silicon? Okay, it is a type of electrically erasable programmable reader memory. So, EEPROM, but EEPROM existed from long time. We did not have flash memory that time, is not it? EEPROM is not really flash memory, because these had restrictions on the storage. You write bitwise there and required high voltage, but in a flash memory you write in a flash several kilobytes of data read and written in one operation. So, these have more efficient and the writing occurs at 5 volts. Earlier in the EEPROM you need a special EEPROM programmer which will generate I think 24 volts or something, right. Much more higher voltage was necessary because tunneling of electrons is required, right. So, here similar principle, but much more improvised, and read and write occurs in large chunks of data, several kilobytes in a flash. So, this is much more efficient, cost effective, and of course, lot many developments have occurred, like rather than just storing charge is present or not present, the quantum of charge is present, that also indicates different levels. So, one cell can store several bits of data depending on the levels that are recognized. So, in all these devices, whether you talk of a camcorder or you talk of a cell phone, flash memory is used as a permanent memory, because these are lightweight, these are consume less power, less costly, right. So, these are the reasons why all these devices we will look at. Whenever we talk of a permanent memory, we will talk of flash memory, and of course, it is much faster than hard disk, because these are after all semiconductor memory. So, let us proceed with the other blocks in this. So, we have some human interface for configuration. We will not really bother in this course about this one. And then we have auxiliary systems which are interfaced to the CPU for controlling power, cooling, all those things, reporting any malfunction, all those. And then we have diagnostic port for running diagnostic applications. And just see here that the signals generated by the external environment are sensed by the sensor, and then the system processes this, and then the actuators are driven, and then this again controls the environment. So, you can think of this part as a loop, a feedback loop, right. The environment is getting controlled. Each time events are sensed, corrective actions are taken through the actuator, and again the change of that corrective action is sensed. Now, look at here that there is a electromechanical backup and safety. If the system fails, wherever possible, so you will see many applications where such a electromechanical backup safety would not be possible, but many systems it becomes possible, and we have this to take over in case this system fails. So, this is one basic diagram we will keep in mind as we proceed. Now, before we get into the nitty-gritty of a real time operating system, the different components of it, features and so on, let us just have a rough idea. We had so far said that there are external inputs, and then there are timing constraints on these, the behavior that will be determined based on the input, and if the behavior or the response is too long, then we will say that the system fails. But using a general purpose operating system, how do we ensure that? Because there might be several types of events requiring different times by which they might be completing. So, the general purpose operating system, we will also examine this issue in much more depth as we proceed, but these can't be used in this kind of applications. So, we will have these real time operating systems whose primary aim would be to help tasks meet the deadlines. How they will meet the deadlines, how deadlines are specified, all those details we will look at later, but just to tell in one sentence, this task deadlines, they are met through task scheduling, proper task scheduling, and therefore, in this real time operating system area, task scheduling is one of the most important tasks. You look at any book or whatever, any discussion on real time system, you will see that it revolves around the task scheduler, that is the crux of the thing. So, we will spend some time on looking at the features of different schedulers, where they are used, what is their shortcoming, how to select a scheduler for an application, because operating systems might give you facility to configure different types of scheduler in your system. So, we will look at those issues. Now, let us look at some basic characteristics of an embedded system. We will keep this in mind as we proceed. So, one thing which we have said quite a number of time, that in a real time system, at least some of the tasks or some of the behavior associated with some time constraint. One example of a time constraint is a deadline constraint, has to finish by some time. Another type of constraint may be start the task after some time. After a lapse of some time, the task should be started. We will see different types of constraints that we will encounter in a real time system. Now, another characteristic here is that just having the result correct is not enough. Suppose the corrective action for a chemical plant, when the concentration or the pressure or the temperature changes, the corrective action that needs to be taken may be correct, but unless it is done at the right time, that won't be correct, right? It will be a failure still. So, we will consider it as a failure. Now, let us look at the further characteristics. Another one important characteristic is safety and task criticality. We will call a task to be critical when if the task fails, then the system would fail. So, any failure of this task, of a critical task, would not be accepted. Just to think of an example, let us consider a robot, and it is moving and encounters an obstacle, and suppose the obstacle avoidance task is a bit late, does not meet the deadline, then there will be a collision of the robo, and we will say that see, the system failed, it could not detect the obstacle and take correct action in time, right. So, that is a critical task. And the other concept here, other than the criticality, critical task, if there is a failure, it will fail, the system will fail, and a safe, let us look at the concept of safety. A safe system is one when it fails does not cause damage, right. If we have a safe system, we will be comfortable that there will be nothing can be really damaging out of it. So, these systems have to be safe, because damage will not be tolerated, right, because this damage can be very costly, are used in life saving applications and critical applications like a nuclear power plant. So, we will see how this will be ensured later, but we are just looking at a characteristic that these systems, criticality is a characteristic, some of the tasks will be critical, safety requirement, and these are called as safety critical. We will elaborate this issue a bit later. We will call these systems to be safety critical, some of these systems, where if there is any failure, there will be severe damage that will be caused. Now, there is another characteristic here, important characteristic, true almost universally across all these systems, that these are concurrent, in the sense that multiple tasks will be active at the same time. All these systems we will see later, multiple tasks will be there and they will be active, but why do we have this requirement? Why is it that there will be multiple tasks? Can't one task be enough? To answer this question, we need to see how these operate. Actually, these respond to events, and the events can be many, like we are saying that there may be pressure sensor, temperature sensor, maybe chemical concentration sensor, or maybe in a onboard system might have to sense the altitude, might have to sense the acceleration, speed, all those things. So, multiple events need to be sensed at different intervals because of the characteristics of the sensors or the characteristics of the events themselves, and then this has to be processed separately, right, handled, and then we will get more idea as we proceed. Now, one consequence of this is that even though the input values are the same, depending on when they occurred, the output may be different. Any concurrent system exhibits non-determinism, or the output will be different based on how these events are sequenced, and in real time system how these are spaced out, right, in time domain. So, this also will keep in mind as we proceed, important characteristic. I hope it is okay, is not it? And as we were saying that these have feedback structure, because the environment is sensed, the events are processed, actions are taken, and the response to that action is again sensed, but these are also distributed in nature. We will see majority of that, large number of that are distributed. Why is that? Because events can occur anywhere, and we need to process those events which have occurred in a over a location, possibly at the same location, and store at the same location, like we are discussing about the SCADA, other applications. Another requirement is a custom hardware for these applications. Do not need a general purpose processor, or maybe general purpose sensor or actuator. We might have to design a specific hardware for many of these devices, For example, if we have a coffee vending machine, if we use a general processor, it will not fit into this because it will be extremely expensive, is not it? Need a small processor there. So, we have different kinds of embedded processors. For example, ARM processors are important category of embedded processors, but you will see that the hardware, we do not use a general purpose board, general purpose hardware many times just for cost consideration, size consideration, specific characteristics. We need only specific part of the processor. So, why do we invest on a full processor? So, these are some of the reasons why many of these are based on custom hardware. So, this we had seen in some form that the sensors generate signals, and these signals are conditioned and read by the processor, and computation occurs, and then the actuator signals are generated to drive the actuators, and there is a feedback nature. So, this is a much more simpler diagram than what we discussed earlier, but let us keep this in mind as we proceed, that there will be signal sensed, computation occurring on this, actuator will act on the environment, and the change in the environment will again be sensed. A few more characteristics. You might also find these terms as you read literature on real time system. One is called as a reactive system. Actually, many of the applications that we use, for example, you are using a Word package, you use it for some time and close it down, right? That is not a reactive system, but a reactive system is one where it just continues to occur over a large period of time. So, there is a ongoing interaction between the computer and the environment over a long period of time, unattended by anybody, just keeps on working for months or years together. So, this reaction between the computer and the environment over a long period of time is called as reactive. This term is used in the literature. If you read a book or a paper, you will come across this term. Another term that we will also use as we proceed is stability. Now, let us get this term clarified, that sometimes events when they occur, we do not have much control. We have control on the system, but environment will behave on its own way. And what if several events occur at the same time? Let us say all these are being sensed, the temperature, pressure, etc., and also there is a fire situation which is monitored. So, several events will get generated at the same time, and can the system process all these at the same time? So, that is a overload situation, and if the system fails under this situation, then we will say that the system is unstable under heavy load. So, this will be an important consideration as we look at the operating systems and so on. We will talk about whether the system is stable under overload situations. Is that okay? The stability under overload situation. Okay, let us look further. Another one will be exception handling. In case some exception events occur, how this will be handled, we will also discuss in the context of the operating system, exception handling. Now, let us elaborate this concept of safety and reliability, because important issue in a real time system. In a traditional system, see, we have these concepts also, safety and reliability in traditional systems, and there we have these concepts of a safe system and reliable are independent. For example, we will have a safe system which is not reliable, and we can have a reliable system but not safe. We had already seen this actually. A safe system, even if it fails, no damage will result. On the other hand, a reliable system, is one which operates for long periods of time without any failure being encountered, then we will call it as a reliable system. In traditional systems, safety, we can increase safety or we can increase reliability without affecting each other. And we can also have systems which are safe but unreliable, unreliable and unsafe, reliable and unsafe, and so on. In the real life situation, can you give an example of a safe system but which is unreliable? Can anybody give an example of a safe system? Yes? Mobile phone. Mobile phone is reliable, isn't it? I do not know what kind of mobile phone you have, but normally these are quite reliable, isn't it? Work for a long period of time, not much failure. Reliable, mobile phone is supposed to be reliable. Anybody has any example of a real life situation? Need not be a computer or anything. In a real life, can somebody tell a system or a artifact or whatever which is weather forecast system, is it unreliable? I mean, it works very unreliable.
It doesn't guarantee that it will.
Okay, I mean, as long as the letters you send, if they are lost, you do not mind, right? Then it is you can say that it is a safe system, because even if letters are lost, it does not really hurt you. Or maybe a email system where emails may get lost, they are getting lost, right. So, this is safe, but again unreliable. Email, no, we have seen it does not reach. But what about the other example? We have seen a safe and unreliable system. Or another example can be that you have developed a word processing software, right, crashes very frequently, like earlier times the word processors used to crash, now they are more stable, and before it crashes it just saves the data. So, you do not lose much, it is only irritation that you need to start again and again, but you do not lose much data, right. That is another example of a safe and unreliable system. What about an unsafe and reliable system? Can somebody give an example?
Cardiac monitor we use in medical equipment.
Okay, unsafe. Why is it unsafe?
Because if there is surgery going on,
It is a cardiac monitor example you gave, right. So, why is it unsafe?
so if a surgery is going on, then if
Okay.
if it fails at that time,
Okay.
the patient can die because
Okay, yes, okay, yeah, right. But there can be several examples. You can just say that a gun, right, very reliable, does not fail normally, but if it fails, or let us say you are firing, it does not really, I mean, it explodes. There is a problem, it happens, no. So, it is a safe and it is unsafe but reliable system. Okay. Now, let us proceed further. In traditional systems, safety and reliability are independent issues. We had seen you can have systems safe, unreliable, unreliable, unsafe, and so on. But in a real time application, which are many of them are safety critical, and in this kind of application, any failure of the system would result in severe damage, right. So, we cannot let the system fail, and also it has to be should not cause damage. Just see here, cannot let the system fail and cannot cause damage even if it fails, right. So, these are called as safety critical. Now, let us see the implication of this. The implication is that safety and reliability are no more independent issues, they are dependent on each other. it has to be reliable and also at the same time safe. Okay. So, how do we get that? We have to have increased reliability, it should never fail. So, one possibility, should never fail. In a traditional system, you can make an unreliable system to be safe by reverting to a fail safe state. Just let us take the example of a word processor. You had valuable data and it was unreliable, but before it crashed or something, it just saved the data, right. So, there is a safe state for that. If the safe, it fails in the safe state, all data has been saved, then you do not lose much. So, it is an unreliable system, but we have made it safe just by transiting to a safe state during failure. Or let us okay. So, a safe state is one where no damage will result if the system fails in the fail safe state. So, if a fail safe state exists, we can convert a unsafe unreliable system to a safe system. We will just transit to the safe state. There is an example here. See, a traffic light controller in road intersection, even if it fails, it leaves the lights orange and blinking. This is a safe state here. Suppose it failed with the lights all green at the intersection, it will become unsafe, accidents, people will rush in. If it fails in all red, that will be unsafe also, isn't it? Traffic will become a standstill. But if there is a safe state like orange and blinking, people know that it is not working, they proceed with their discretion. So, we will also use these terms, a fail safe state, safety criticality, safety and reliability, all these terms we will use it. I hope these terms are clear. Okay. Okay, this we had already seen that for a unreliable document processing system or a word processing system, the fail safe state is saving the document in the disk. So, a fail safe state actually helps to separate the safety and reliability issues. Because we can have an unreliable system and we can make it safe, right. But unfortunately, in real time systems, safety critical systems, we will see that there are no fail safe states. Otherwise, we will not have much problem. Even if it fails, we will change it to, or we will make the system fail in a fail safe state. Unfortunately, for this system, as we will see shortly, fail safe systems do not exist in a safety critical system. Okay. So, an unreliable system can be converted to a safe system. Unreliable and unsafe system can be converted to a safe system just by making it fail in a fail safe state, right. Now, as we will see, the safety critical systems, there exists no fail safe state. If it was a system where fail safe states exist, and even if it is a critical system, could possibly have we would have changed the state to a fail safe state and no damage would result. Now, let us take an example. Let us say there is a autopilot system and the plane is flying and suddenly the system fails, right. Then what will be the fail safe state? Would shutting down the engine help? Would no, it will still fall, isn't it?
It can be taken over by manual pilot.
Okay, but if the manual pilot exists and he can control, but many of these autopilot, they just fly by themselves, and sometimes it is not possible for the manual pilot to take over a plane. For example, let us see this plane, supersonic commercial plane. Have you heard of this Concorde? Anybody heard of Concorde flight? So, it was a supersonic flight operated between, I think, London and New York. The normal planes would take something like 8 hours, and this is a supersonic commercial plane. See, we have seen supersonic planes at the jet fighter planes and military applications, but this is a commercial plane, and used to operate 4 hours it used to take, and then just crashed, and they just said that the autopilot system failed, but nothing could be done. It flies at that speed, and a large aircraft, even if a pilot is there, he will be a little control. He can control such a large plane. The kind of response time, etc., will be required at that speed will be difficult, isn't it? So, for such systems, the safety critical system is not even asking for the manual pilot to take over, right? Okay. So, for a safety critical system, the only way we can make it safe by making it extremely reliable. For 1,000,000 flying hours, one failure, 1,000,000 flying hours, right? That is the requirement of the Federal Aviation Agency, extremely reliable. Okay, let us proceed further. So, just to summarize what we discussed, a safety critical system is one where any failure can cause severe damage, and no fail safe state exists in these safety critical systems. So, can't even revert to a fail safe state. So, the reliability will be increased only through, the safety will be ensured only by increasing the reliability, making it extremely reliable. But the question is that if you want to develop a highly reliable system, how do you do that? Let us not worry about hardware, because that is not our domain. Let us see, as far as software is concerned, how do you develop a extremely reliable software? Yes, anybody would like to answer? How do you develop extremely reliable software?
By considering all the possible error causes.
Okay, testing. Okay, he says testing. Yes, we have to test them, but we know that testing does not really reveal all problems in a system. Even after you are thoroughly tested, you can't guarantee that there are no problems. So, what do you do? Testing, yes, you have to test it very thoroughly, correct, but that do not really solve the problem.
So we can use a development methodology like some model.
Okay. Yeah. So, to reduce the scope of error, you can use some methodology which will reduce the chances of errors, but still there will be some errors remaining. You can't guarantee that there are no errors in the system. For large systems, at the present moment, it is impossible to guarantee that there will be no failure. So, in case of a failure, you will have to provide for fault tolerance. Even if the system fails, there should be some mechanism in the system which will, in the form of a redundancy possibly, that it will take over, right. Even if the supposed to have failed, another thing will take over and it will not really fail. So, let us see these approaches. So, one is error avoidance, as he was saying there, that we can use some systematic methodology where we reduce the chances of error, we avoid errors. The other is testing, detect errors and then we remove the errors, test it thoroughly, and still there will be chances of problems. because we can't really test with all exhaustive values. There are too many of that to be able to test in a reasonable time. So, we will have to have fault tolerance features in this kind of safety critical systems. Even if no, fail safe is a state. Okay, let me just repeat his question. Says that the terms fail safe and fault tolerance appear to be confusing. That is the question. See, fail safe is the system fails, but while failing it just fails in a state where damage will not occur. But in fault tolerance we are saying that even if there is a problem somewhere, we are masking it by some means, and how we are masking is through redundancy. For example, it is very easy to consider the case of a hardware, a processor malfunctioned or a sensor malfunctioned. We have another redundant sensor, we will just reconfigure that, the processor takes over, and even though one processor has failed or a sensor has failed, we will not really notice that. For the operation, it will make little impact even if the processor that was working that really failed, because another extra processor has taken over. So, that is a example of a fault tolerance. Is that okay? Okay, let us proceed. Fault tolerance in hardware is very intuitive. If you talk to persons working in the hardware area, they say that yes, the hardware that we develop are fault tolerant, and there is a standard technique called as triple modular redundancy, built-in self test. So, you just find errors and then you invoke another one, or you do a voting, right. You have 3 redundant pieces all working at the same time, and then if one of them fails, the other 2, the results will differ, and you know that there is a failure, right, and then you remove that one which failed and use that majority result. Standard technique, triple modular redundancy, the standard hardware fault tolerance techniques. But we will see that in case of software, which is the our current discussion, it is a very tricky issue. Let us see what are the approaches to fault tolerance in software and what are their problem, because we have to keep this in mind as we proceed. See, we had seen that the idea behind any fault tolerant system is to have some form of redundancy, maybe redundancy of components, redundancy of programs, or maybe redundancy of some activity. In a hardware fault tolerance, we can easily mask the fault of the hardware, as I said, with triple modular redundancy, but the fault may be due to software, and that is more likely, because hardware nowadays are so reliable, they hardly fail. But even if there are chances of failure, we can provide fault tolerance in hardware very easily. But if the fault is due to a software, even if you have hardware redundancy, all those, nothing will work, right, it will still fail. So, how do you provide software fault tolerance? There is a bug in the program. How do you really provide fault tolerance feature in software? Anybody would like to answer this question? I am sorry, can not exception handling actually. See, the let us say the program has gone into an infinite loop. So, what do you do? Exception handling is not really fault tolerance. Anybody else would like to answer?
Like in the case of distributed systems, if one system fails due to some software, other system catches up the problem and it goes.
No, but the software running is the same, isn't it? Even in a distributed system, the same software will run there. So, there is a bug and it will fail again for the same reason.
Sir, can we have a monitored program sort of? If the time exceeds the limit, then
No, how will you overcome? See, again if you run that software, again that problem will come up. and you run another copy, that problem will be there. Like he was saying, in a distributed, we have another copy which will run, but again that problem will come up. Okay. So, there are two standard approaches to software fault tolerance. Now, let us look at these approaches. One is called as inversion programming and the other is called as recovery block, two very popular software fault tolerance approaches, used also in practical situations, but we will see that not effective. Software fault tolerance still remains a very challenging issue. No really good technique like hardware fault tolerance exists. Now, let us look at this inversion programming. Actually, the inversion programming is based on the hardware redundancy technique of triple modular redundancy, or TMR. In a TMR, as we are saying that there are redundant components, 3 of them we have, even though one could have served, we have 3 of them repeated, and we take the voting of the results and use the majority result. Now, this is extended to the software domain. How do we extend this to the software domain? In software domain, we create different versions of the software. We have independent teams that are working. So, the same problem, 3 different teams, they are developing 3 versions of the software and hoping that they will not commit identical mistakes in their code or their algorithm. They might use different algorithms also, right, because they are working independently. Hoping that the different versions of the software will be different, we can make them work at the same time and then take the voting, but again is not a very effective technique. Unsatisfactory performance. Why is that? Actually, even if we have independent persons, independent teams working, but when you actually run them, you find that the faults or the under the conditions they fail are identical or the faults are similar. Why is that? Because teams were different types of people working at different places, they do not even talk to each other. No, input is the same, but like let us say programmer committed a mistake and there we have a different programmer, he might not commit the same mistake, but we are finding that they are failing in similar reasons. Why is that?
Because a program is normally tested, so the programming bugs are likely to be removed, but there can be bugs at the design level which are not removed even at
No, designed also differently. The different teams, they do their design requirements, they do their coding testing independently.
Because they are following the same programming methodology.
Need not be, they might use different program
but
methodology.
It is not related to the complexity of the module.
Yeah, maybe that is the answer. See, the thing is that even if the programmers are at different places, they are working without talking to each other, but the part of the program where one team finds difficulty and likely to do mistakes is the same for any other team. They find that the same modules are difficult to code and their errors remain, right. So, maybe for that reason the inversion programming is not very effective. I mean, it might work for some simple programming errors which one team committed, another team did not commit, but for majority of the errors it does not work actually, because these are identical errors in the different versions of the program. Okay. Now, let us look at the other technique, the recovery block technique. Here we have different a task is divided into try blocks. Okay. So, one task is divided into 4 try blocks. okay, let me just correct myself. These are not the task is not really these are not really TB1, TB2, which are the tri blocks. These are not really division of a task into these 4 blocks, but a task is divided into 4 or maybe more blocks, which we do not see here. See, these tri blocks that we see here are same tri block, right. I mean same type of programming, same part of the task they are doing. These are redundant copies again, but the thing is that only one operates, tri block 1 operates, and then the result is tested. If it is a failure, try to use another tri block, again the result is tested. So, here just see that they are not really redundant copies or different versions, but these are different tri blocks that are run one after other, and in a real time situation, by the time the tri block 1 is completed, it takes some time. So, you have still less time remaining to try the other tri block. So, possibly you can have a simpler algorithm here, or maybe you can sacrifice accuracy or something, and these use deliberately different algorithms. So, this is also another way to provide software fault tolerance, but again the same problem, correlation of the errors and is not very effective. Yeah, right.
If all the 4 blocks are having the same code,
Yes.
if one fails, then it's obvious that the other also failing at the same point. How are they providing fault tolerance?
No, see here the tri block 1 is the actual module, right, and we test it. If it is a failure, we try a simpler algorithm, which is using a different approach, different algorithm, deliberately different. Each tri block is deliberately a different algorithm. Sorry?
Similar to inversions.
In inversion, we do not say that they are different algorithms. We say that independent teams, they might use the same algorithm, it might be standard, they just do not talk to each other, right. So, maybe if it is a standard let us say a quicksort algorithm is used by one team, the another team might also use the same algorithm, because that is the most effective at that time, right. But here we are saying that do not use the same approach, deliberately use different approach, and of course, these have to be progressively simpler algorithms with sacrificing accuracy, because time is becoming smaller and smaller, right. The time remaining to complete is smaller and smaller, and once we have these tri blocks, if there is a, we can also restart it. That is one thing that we need to understand, that see the input has been processed here, but we can, the tri block 2 can be restarted, because we have to recover, we can go to a previous state, a recovery state, and from that state we will try the tri block. So, each tri block after completion, we will have a recovery state where we just store all the results. We can always go back to that state and then restart, right. That is the idea.
So in this one, the TB2 should get the input rather than the result from it.
Okay, we have, what we have showed is TB2 in case of a failure is invoked. Okay, I think there is a inaccuracy in the sense that it will revert back, it will recover, I mean it will go back to the previous state. So, we will just stop here, and we will continue in the next lecture.